project a short little problem, just sort of pencil and paper calculation that gets at some of the ideas that I presented in the lectures of the past, of yesterday and today. Here it is. I don't know how to, can I make it full screen? I don't know how this works. Here. There, you can see that, right? So this is just a little sort of problem set kind of a problem, which you can take a look at. For those of you who are interested in this kind of stuff, try your hand at this. Feel free to talk with me in the back of the room. I'll be around and ask questions about it, or we can work on this together. There's also sort of more complicated, detailed problems that we can get at that would involve, writing a little computer simulation of the sort of dynamics that I was talking about yesterday or today, and asking some questions to compare the simulations to the sort of theory that I was talking about. So for those of you who are interested in that, you can start with this and talk with me in the back. What we want to do, though, is spend most of the time, or most of the focus today, on a practical data analysis problem that John has prepared. So I don't know, do we want to leave this up for just a minute for people, or we can alternatively, I don't know if it's possible to print things out here, is it? Okay, so I'll email it to these guys. This is sort of what it is. I'll email it to these guys, and they can try to print it out for those of you who are interested. Or if you want to take it home and look at it later, if you want to work with John now, you can either talk with me tomorrow or email me later about how it works. Okay. So that's my 3 minutes. For the exercise that I prepared, it's a chance for you to get some experience looking at some real data using a fairly impressive data set that's available online from the Human Genome Diversity Panel, which is a set of SNP data from 52 populations across the globe. And before I say more, though, let me just introduce you to the files that I distributed. So you should have this directory, HCDP, popstruct, exercise, short version. And it has, you won't have this answer key directory, but you'll have the two directories, doc and results, and readme.txt. Okay, if we open up the README, it has just a short description of what you have here, with the doc directory containing a PDF file with the documentation. It also has, and I'll show you this, a .r and a .sh file that has all the commands that are used during the workshop exercise, with the idea being that you can cut and paste from those files, they're flat text files, and run the commands. So that way you don't have to retype every command, okay? And then the results files has the results from running different programs, and I've gone ahead and run them and just left the results there for you so you can plot the results, okay? If you'd like to actually run those original commands, there is a more full-blown, oh, that's awful. There's a more full-blown version of the of this exercise available on my GitHub page. Can anybody open the README file that you have there? Does it have the links there? Okay, good. Somehow I erased the links off of my copy here, but in your version of the README, it's got the links to the full version of the exercise on the GitHub page, or via a Dropbox link that should get you the files. Okay, but for limited time, and because we're all going to be working on our laptops, I've made this compressed version. And so let's look at the doc directory first, and where we have, mine has a few extra files, but you should have a PDF that describes the workshop, then these two flat text files that
have the commands that you're going to use. I might recommend when you open this, since you're only going to be using the R part of this, you only need to open up the workshop commands.r, and you can open this with, if you're in a Mac system, you use open with and something like text edit, a flat text editor, and it will have the commands that then you can cut and paste into the R window, or you can directly open this within R and cut and paste from there. Okay, but we'll get there in a second. Let's look at the PDF file for a moment. Okay, and what I wanted to do here is create an exercise where you can see every step that was involved in the analysis of the data, so that you can steal a lot of commands from this file and use them in your own work. But it's also pedagogical, and so you know, in this version of it, there are a lot of these steps that I want you to skip. Okay, but if you want to see how they are done in more detail, you've got them here. So first, I described the data set. Okay, this is from the Illumina 650Y SNP array. So this is a genotyping technology that genotypes about 650,000 different SNP markers, and it's been applied to the Ceph Human Genome Diversity Panel, 52 populations in total. The data you can get directly from a website at Stanford that's given there, okay? And there's been some initial quality control filtering to remove SNPs that look like they're suspicious in terms of the quality of the calls. And then I've filtered down the original data set to a set of 938 unrelated individuals, okay? And then I've, if you download the full version of this workshop from those links, then you would have the data files in a format that's a binary format, so it's compressed in a binary form that is a format associated with a program called Plink, which is a very popular and useful piece of software for doing a lot of low-level manipulation of genotype data. Then what have I done to get this thing going? I've subset the data to just look at the European subset of populations. And I apologize for being Eurocentric. I first developed this for a workshop in Sardinia, so that's part of why there was that focus. And then I filtered out SNPs that are in linkage disequilibrium using some commands that are available in Plink. And then the first exercise is to explore Hardy-Weinberg predictions, which in actual data, so these p squared, 2pq, q squared, does it, is there any actual, does biology look like that at all? We talk about how simplistic the assumptions are behind it. We'd like to, actually look in data and see how well Hardy-Weinberg holds. And I also want you to explore specifically whether you see a deficiency of heterozygotes, the Volland effect that we talked about in both Michael's lectures and my own, that when we have subdivided populations, a symptom of that can be seeing fewer heterozygotes than predicted by Hardy-Weinberg. And so you're gonna see if that arises in data using two versions of the data. So in the first round of it, you're gonna look at Hardy-Weinberg predictions using just the European data, or actually no, using the global data, so all 52 populations. Then in the second round, you're going to use the subset that just is the European data. Okay, and so just right off the bat, we have some prior on whether which one is going to have more substructure, if we look at the whole globe or if we look at Europe, okay, alone. And so I've gone ahead and used Plink to get basic genotype counts using a command called --hardy in Plink, which will produce will compress the data down to just having a single file with the genotypes counts and tests of Hardy-Weinberg equilibrium. And then and those files have these HWE line file extensions. So let's look at, if we now go into the directory that has results, Hardy-Weinberg equilibrium, we're going to see that we have the Europe file, and then, so H93 underscore Euro is the European file, H938 just dot HW reduce is the whole data set, okay? And these are just two log files that are outputs of Plink when I generated the files. Okay, and then, if you like, you can look at those files in more detail. They're flat text files that summarize the data. Maybe I'll show you that real quick just for education's sake. So let me just get to the right directory. So I find it very useful, and as many computational people do, to work from the command line, because there are commands like head that will show me just the top of a file. So let's look at the top of the H938.hwe reduced file. And what we see is that it has, you guys see that? It has one line per SNP. It has the two alleles that are present, and then the counts of the three genotypes, the 34 of one, 210 of the heterozygote, 694 of the other homozygote. And then it has the observed heterozygosity and the expected heterozygosity, and then a p-value for the test of Hardy-Weinberg equilibrium. What you're going to do is use R, a script in R that's going to read out, that's going to strip these genotype counts out of each line of the file, and then manipulate them and make a plot that represents whether there's Hardy-Weinberg equilibrium or not. Okay, and so there's a single function here that's this large function plot genotype versus Hardy-Weinberg in terms of Hardy-Weinberg expectations, and it's long. I don't recommend cutting and pasting from the PDF because you'll straddle the page break, and it's been fontified to look pretty here and readable in the PDF. But to actually cut and paste this into R, you should do it from that flat text file that I described earlier. So how are we going to do this? We're going to, there's a few steps, and I'll walk you through these. When you're working in R, you've never done it before, there should be some version of a console with a caret marking where we can put in different commands. So for instance, I can put in a command to generate 100 normal random variates. I'm not sure why it's giving me warnings, but anyway, we can put in commands here, okay? And the these are, yeah. Okay, and there's a notion in R of a working directory, and so we need to be in the right working directory to read these files. And so there's, in the versions of R on the Mac, there's a session tab, and you set the working directory by choosing the directory, and we're going to choose to go to, I've got to navigate to where the results are. So here are the Hardy-Weinberg results, and I'm going to set my working directory to be that one for this part of the exercise. Okay. Now I'm in that directory, so when I go to read files, it's going to look in that directory for the files, and it should find them no problem. Okay. In the Windows version, it's under File, and it says Change dir. And that's how you change your working directory. Okay. And now what we're going to do is go to the, I'm actually going to, within R, you can open files. And so I'm going to open the workshop commands.r file. So now I have that open, and I'm going to take, this is, you can read the instructions for this in the PDF, but I'm going to just help us along because this first step is oftentimes where people, first have their first hiccups. I'm going to select, this is a large function. It's defined here that we're going to have a function titled plot genotype versus Hardy-Weinberg, and it starts here, and it ends, it starts with that open brace, and it ends all the way down here with a closed brace at line 37. I'm going to copy that, and I'm going to paste it in here to define that function. And then I have these 3 lines which say, open up a PNG file, make the plot, and then close the PNG file. And it takes a second for it to make the plot, and then it finishes. And then if I go into the directory now, I now have this plot. The legend got a little garbled, but it's basically all there, okay? And I won't give away the punchlines. You'll need to, there's a set of questions for each section of the exercise that you can answer, but let me just say that what that plot is doing is taking for each SNP, calculating the allele frequency, and that determines where on the x-axis the SNP is going to be plotted, and then a point is put down for what the frequency of the homozygote allele is, the frequency of the heterozygote, and the frequency of the other homozygote is. So we'll get 3 dots for each SNP that correspond to the 3 genotype probabilities for that SNP. Okay? And in the dashed lines, we have the Hardy-Weinberg expectations. So p squared should look like half of a parabola, right? And we have the p squared, we have the q squared, and the 2pq, okay? And, you can think about whether that's a good fit or not. In what ways is it, was it not matching what you'd expect? And you're going to compare that to what you see when you see the European data as well, okay? This is from all of the SNPs on chromosome 2, actually. I should have mentioned that. I've subset out a set of the SNPs so that we're not looking genome-wide at this point. There would just be too many points. So we've subset it on just a subset, a selection of the SNPs in the whole data set. I can't help but say, I think it's pretty amazing that you look at data and it looks, these p squared, 2pq, coarsely speaking, the SNPs are following the pattern, right? There's some deviation. I wonder why. Some effects we've talked about that you can think about more, okay? But, okay, so so that's the first part. So you're going to do that once with the full data set, then once with just the same file, but now for the European subset. You're going to answer some questions here. There's a section here about then where you move on, and in a similar way, using the R code that's given, you're going to, if you like, on this one, compute and plot a minor allele frequency spectra. So this is the number of sites that have each of different possible frequencies. This came up in various lectures. And so you'll look at what the frequency spectra looks like relative to the theoretical expectation. Keep in mind that this is a SNP genotyping array. So the SNPs are not a random selection of SNPs. They've been chosen to be put on the chip because they're typically common variants that tag other variants. So that's useful to think about as you interpret what you find there. And then the next sections, and you can go as far as you want with this, but is I've run admixture on the data and left the results in the results/admixture subdirectory. And there's code for plotting those results and looking at the answers. And then there's also, I ran PCA on the data, and there's code for plotting those results as well. And then some questions about interpreting the data. And so you end up with a total of 14 questions that you can answer. There are a few suggested follow-up activities. And then for complete transparency, because this is just about learning and not about grading, the answers are all at the back. So try not to look at them, but I don't want you to be stumped after I leave here, and you've got them there to help you with this learning exercise, okay? What else do I want to say? Oh, one thing I'll say, the populations that are in the European data set, you may not be familiar with the names, so let me just say a little bit about them. I'll find a place where I have them labeled. Yeah, okay, so maybe I'll sketch really quick. I should add this to the documentation, some kind of background on the populations, but if this is a crude representation of Europe somehow. Something like this. Okay, can you see Spain here? Can you see Italy? This is Africa. North Africa. Is that okay? Okay, so the populations are the Orcadians, yeah, from the Orkney Islands. So if you're a fan of Scotch, you might know of the Orkney Islands and the fine scotches that are made there. And so this is a isolated population from these islands at the very tip of Scotland. Then there's a sample from the Basque, a population from the mountains between France and Spain, who are thought to be very isolated. They speak a language that's hard to interpret in terms of its relationship to other Indo-European languages. There's the Sardinians. So this is the island of Sardinia in the Mediterranean. It's a mountainous island with a lot of different villages that are separated. Then there is just a non-isolated population of French, a non-isolated population of Italians. I don't need to mark those. And then the Adyegi, more isolated population from the Caucasus Mountains. And I think that should be all of them. Okay? And so when you look at the admixture results, what I'm going to have you do is look at results from admixture where it's been run with K equals 1, 2, 3, 4, 5, 6, because that would be a good starting guess for how many subpopulations there are. And then you're going to investigate. Does it actually separate them out as 6 different groups, where the groups correspond nicely to each subpopulation? Or do you somehow see some populations that are grouped together and other populations that are split apart? And then you're going to investigate the same data using PCA and see the ways in which the admixture results and the PCA results differ, and ways in which they're also telling the same story. Okay. That's it. And I think we were saying that we were just going to let, it's already been quite a long several days. So if some of you just need to step outside and see some sunshine and want to work on this later, that's perfectly fine with us. If some of you want to stick around, I think we'll stick around at least for some period. And as long as there's interest, we'll stick around and help with any kind of hiccups with using R and interpretation questions. But yeah, if you decide to disappear and want to work on this later and then just email questions, that's perfectly fine too. So you could